Welcome to the Future of Supply Chain, presented by Dynamo. Each episode, we sit down with leaders in the industry as we build the future of supply chain together. Let's get into the show. Here's our host, Santosh Sankar.
Hey, ladies and gents, welcome back to the Future Supply Chain Podcast. I'm your host, Santosh Sankar. Joining me today is Matthew Putman, CEO and founder of Nanotronics. Welcome, Matthew. It's great to have you on the Future Supply Chain.
Oh, no, I love talking about supply chains. Thank you.
Absolutely. And, it's not often that we get somebody from the semiconductor industry who can also geek out around supply chain topics. And with that, I would love for you just to share the quick 90-second skinny on what Nanotronics is and what you and the team are building.
So Nanotronics, we're a hardware and a software company that tries to enable manufacturing to move to the next generation. And we do this through a number of means, but mainly by using generative AI techniques, things that we're seeing in our daily lives with things like ChatGPT, but we're seeing what's the foundation of it? How are those things made that enable all of these consumer applications to occur? So we do this by helping companies improve their yields, lead to faster iteration of new products. And, we even make small fabs in order to make new types of devices that just are not seen in the world, but are necessary if we see technological advancement going the way that it looks like it's going.
And what's the Matthew Putman story? How did you get into the wild, wonderful world of manufacturing semiconductors?
Well, we talk about semiconductors, but I think about sort of manufacturing as a whole. It's the building of everything in our lives. And my story goes back really far. I worked in manufacturing when I was 8 years old. My father started a company. Actually, both of my parents started a company that put the first personal computers onto factory floors in 1982. And we're doing testing and doing things that are like, 1980s version of what we're trying to do with AI. They were doing with compute when it was analog before. So I was so lucky as a kid. I got to spend time really learning about quality control, learning about process control. And that was it. That was in the chemicals and rubber and plastics industry. So nothing to do with semiconductors. But it made me extremely excited about how you scale new materials and how you take older industries and modernize them. So I had this background of living in factories as a kid. Later in life, I ended up running that business, and that was acquired. I worked as an academic for a while, and found this frustration as an academic that you'd have these great discoveries in a lab, but my heart was always still in the factory. So our great discoveries in the lab may not make its way into the world. And so when I talk about getting into semiconductors, it's really a sort of special branch of semiconductors 14 years ago, which is these things that are used for power devices, LEDs. At the time, LEDs were a big deal. They still are, of course, but what are the next generation of photodetectors, quantum computing, the things that were just on the cusp of becoming commercialized. And we were seeing great results in a lab. Our goal to start Nanotronics and my goal in life is to see these at scale. So I'm a material scientist. So looking at rubber or looking at a semiconductor material was a bit of a change for me, but for an AI, it's exactly the same. So now we have this great tool where it doesn't matter what you're working with, you're helping to scale it and get it out into the world.
And we're going to jump a bit more specifically into your background in a bit, but I'd love to kind of take a step back, right? And for our listeners, taking them on a brief journey or primer, if you would, on the state of manufacturing chips, semiconductors in the US. Because if they're to open up the paper on any given day, they're probably reading headlines, they probably see it in the news. But I'd love to kind of help them understand, hey, where did we come from? How did we get here? And what actually is here mean?
Right. Well, the United States were the innovators of modern semiconductors. This goes back to the founding of Intel and, really, creating what is our modern life. However, in the meantime, the production capacity has gone elsewhere. So we had innovation and we lost some of the edge in being able to control the production of that. And there was something going on at this time, and this is really semiconductor history. Is everybody's familiar with Moore's law? You're packing more transistors into a smaller space, and they're getting cheaper as you do it. And this has continued, but as this has continued, there is a trade-off, and the trade-off is that the price of the factories, the price to manufacturing, also has an exponential component to it. It grows exponentially more expensive. So now you have things like fabs that cost $18 billion up to $80 billion to build. So the barriers to entry, once you start to lose some of your ground in production, the barriers to entry become very high in the traditional semiconductor business. And so, we're trying as the United States to catch up a bit. There's the CHIPS Act, which was introduced. So there's some federal money going into this. There's some state money. There's certainly a desire for the larger international semiconductor companies to open in the United States. But it's now what was original to us is new to us again as a country. Mm-hmm. So we have to figure out new ways of doing things, not just throwing money at the ways that others are doing it. And that is by exploring new materials that are less expensive and faster to manufacture, new types of actual physical structures for doing that, people that have different types of training, because we have a workforce that needs to be completely retrained to work in this modern semiconductor environment. And we think that the major contributor to being able to scale American manufacturing of semiconductors lies in the intelligence in the factory itself. So if you have artificial intelligence aiding this workforce, improving our yields, and making improvements to semiconductors, you can start to be competitive and do things differently than everybody else has. And that could be wonderful for the United States. And I can see it in our near future.
Amazing. And the one thing that you all are working on that's really revolutionizing the fabs is this concept of the cube fab. Could you expand on that and describe that in greater detail for us?
Yeah, I mean, it's perfect timing after your last question. So, we looked at this problem of the fact that it takes 5 to 7 years to build a fab. Technology moves faster than 5 to 7 years. So we wanted to make a physical structure that has all equipment and utilities, everything that is required to make a fab in 1 year. So we do this through modular design. We do it through numerous partnerships. But the biggest thing we do is we say, all you have to do is put a piece of software on this to run. And that software is generative AI. And if you take this combination of a building that you could build fast, you can also build it much less expensively because you're not using these older processes that are extremely expensive. And you combine that with the latest of artificial intelligence, you get a factory in 1 year that are making things that are most needed for the infrastructure to be able to see this technological growth in things like electric vehicles, things like data centers that are already taking up a huge amount of energy in the world. How can we save energy? We can make these kinds of chips that couldn't be made before in a cube fab. And that's sort of step one of cube fabs. The rest of the step is this is just a new way of doing distributed manufacturing. It's a network of affordable factories that can be put next to a source, can be put in an urban area or out in a brownfield or greenfield location. But it brings the means of production closer to the end user. And you can work in this sort of new type of globalism where you're sharing across a network. So it's a very ambitious project, but it's not only achievable, we've proven out all the pieces of it over the last 14 years to get to the point where we really realize this big dream.
That's amazing. The one thing, or there are a few things that you touched on, but the thing that really I think resonates is we at one point we had an advantage and a global lead in not just the design but also the manufacture of this product.
Right.
Over the years, we retained the advantage around design, but we yielded the manufacturing capabilities to those overseas. Now, predominantly Taiwan. That's why Taiwan oftentimes kind of gets into the headlines as geopolitics gyrates around the Pacific. But in order for this to return, you've touched on a few interesting things. One, reskilling, because these skills don't necessarily exist amongst the frontline labor force. But even if you reskill, you need to actually adopt a more novel approach where you're testing, or rather, you are questioning the conventional norms and thinking of new novel ways that are more efficient, whether it's a function of time, resource, capital, but also there's a function of automation. It cannot just come back as it left. It needs to come back better than it is overseas.
Yes. And the first thing you said and the last thing tie very closely to each other. The reskilling is we want to reduce the amount of reskilling necessary and open up the world of working in the most cutting edge technologies to people that don't have to have a PhD in electrical engineering in order to work in a fab, which has been very much the way that things have gone. The reason why you don't have this reskilling is that you now have this partner in a fab, which is the artificial intelligence. So the automation part of it is more than automation. It's a tool for those that have not been skilled in the art of making semiconductors, allow them to use their creativity to come up with design ideas, new types of applications that mean something to them, and then have an AI perfect a process to do that. So it opens up the world to a lot of new types of jobs for a lot of different types of people, and at the same by using this modern automation. I don't. The other part of your question, I'm sorry, I missed the other part of your question.
I'll actually kind of push us forward here because you also mentioned the CHIPS Act, and I revisited some of the latest sentiment around the CHIPS Act from this year. And there's been a lot of criticism that a lot of this federal capital or federal dollars have been concentrated to a lot of the incumbents, right?
Yes.
That originally yielded their advantage and are now trying to get it back in part with the support of the government. What's the real take? Like, how do you feel as somebody who is trying to pioneer kind of this next generation or the future of manufacturing in this industry?
Well, I mean, I agree with this sentiment that if you're only funding those who have the large companies that have given up the ability to manufacture, are you just repeating mistakes that you've made before? That does concern me. That said, if those dollars, if it works, if the leadership in those big companies are willing to innovate, that's great too. I want to see the semiconductor industry succeed in the United States. So, it can be a frustration to me that new ideas are not the ones that are immediately funded. You should be looking to the future, not looking to those that are just happen to be big companies that have been around in the past. So I agree with that initial sentiment of yours. But at the same time, however the CHIPS Act money is distributed, let's make sure that the most novel technologies are being used by those companies to do it better than it was ever done before. So I'd like to help enable either.
And when we say kind of bringing back semiconductor manufacturing to the U.S., I would assume that it's a natural progression. Are there certain types of chips and markets that are best suited to be served today versus, let's say, a decade from now as there's more maturity in this kind of renaissance, if you would?
Yeah. I mean, so I maybe take a little bit of a backwards approach to this. If you look at the way that semiconductors for GPUs and CPUs are made, there is not a technology right now that exists that is more advanced than what you're getting out of TSMC in Taiwan. The idea is not to replicate that or even immediately necessarily replicate the desire to make GPUs and CPUs. That will come and should come. We can't be completely reliant on the core processing of our computers from one source. However, there are a lot of needs that are not being met even by other countries. So we focus, our first focus is on novel materials, something called gallium oxide, that has the best electrical properties for energy efficiency that is available. These materials have not been able to scale in the past because it was hard to make, because it didn't have AI to make it. But it's not hard to make as far as the equipment and the facilities required. It's actually much simpler. There's many less steps required than making a GPU. However, the need is equal. So, many people have pointed out that one of the biggest bottlenecks to being able to continue to scale generative AI is that data centers suck up enormous amount of electricity. This is something like 5% of all electricity is already in data centers. If this continues, imagine 20% of the world's energy being consumed
Sure.
by data centers, just data centers alone. That's not including electric vehicles and everything else that we'll be taking from the grid. So
Yep.
we're saying the infrastructure of the AI generation boom or next generation technology in general has to be one that is energy efficient. And we make chips that allow that to happen that nobody else has made before. So that's just talking about us. But there are a lot of parts of this infrastructure that need to be built. And most of those things are semiconductors of some type. So you build an infrastructure around it. You have then new processes being invented to make something like a GPU less expensively, more efficiently than it's currently being made. Then you see a bunch of new ways of doing things, distributed factories, AI-driven factories, and a rollout of infrastructure chips.
Mm. And now, in a parallel universe, as a VC, we're observing a lot of capital going into manufacturing technology, right? Broadly speaking. For the entrepreneurs who are listening, where are there opportunities when you kind of step back, right? You opened up with a lot of kind of how you look at the world is through the lens of manufacturing. You now have dedicated your life to improving U.S. American manufacturing semiconductors. But where are there
And
gaps and
worldwide, by the way.
opportunities? And worldwide.
I
But like where's the next Matthew Putnam who has this kind of entrepreneurial spirit looking for the next thing? Where might they kind of poke at in order to help improve this overall industry?
Well, the great thing and the troublesome thing is that manufacturing is not optimized at all for the most part. I mean, we're certainly working on it, and we have optimized some factories, and we have 200 so customers, and they iterate towards better optimization. But I think that people can start to have more of a creative design mentality than they currently have. It's now humans are like the prompt engineers for ChatGPT for building new things, and we give and now that equipment, I say we, I just mean and I don't want to give too much credit to myself here, but if you can have greater expectations of your factories to make those things that you care about the most, and that could be a number of things for a number of people. That one thing that we're looking at is how can you do climate modeling better? Now there's many reasons to do that. These chips that we're making, one of the things we make is a photodetector. Somebody should be working on this. We've had one on a CUBE satellite. If you had a full constellation of CUBE satellites that had just this detector, you can map the entire globe and measure both what comes from the sun, which is what we usually do, because what goes back into a layer of the atmosphere where you have particulates that lead to warming and cooling. And then you can start to actually do experiments to try to improve the environment, when right now we don't have that. We don't have an understanding of that. This is very important to some people. It's important to me, and I think that there's a lot of room in climate science that could be explored through new types of semiconductors. I think that there's a lot of interesting space in the future of agriculture, for instance. There are ways to create vertical farms that are more efficient, faster yield growth, so you don't have to take up as much land for things that currently are wasteful and expensive. That is one exciting area, and we could really go on and on about all the potential that looks like 10 or 30 years out, that we can start to think, no, let's do this in 12 months. I was on the phone with a university before I got on the phone with you, and I'm just excited about a new way of looking at the path from academics to production. If you were a PhD student, you may be doing amazing work, and it may be very important, but you may never see that out into the real world, or you'll see it in 5 years. The goal is that creative work that you're done, even while you're a student, you can start seeing rolled out into the real world. This is a new thing. It's certainly a new thing over the last 70 years. This is not the way that academics to industry have worked. I'm excited about that, and it should be really exciting to students and professors who feel trapped inside research instead of inside of factories.
I think that's an extremely interesting way to look at things, because you're also seeing some of the larger universities in the US over the last, let's call it 5 to 10 years, very large, well-funded research institutions who are trying to build a muscle around technology transfer and playing a role around kind of this entrepreneurial movement, where they might be sitting in the middle of a once-in-a-lifetime shift as to how one can kind of retain and remain in an academic environment, but that doesn't mean they necessarily need to forego some of the ambition they have perhaps on the commercial side of things.
Yes. I mean, how cool if you're working in academia and you're doing you're working in regenerative medicine, and it's something that looks far out, and then there is actually a facility to be able to do something in regenerative medicine. What if you're doing something in genomics? There are all of these opportunities to say, I'm not just a researcher. My goal is not to publish the next paper, but to see the products that I'm making out in the real world. It's a different incentive. And it's one that the universities have not done particularly well with in the past. But I think, like you said, are starting to acknowledge, if this process gets more streamlined and they have some place to go, like a CUBE fab, to be able to realize their dreams, all the better.
What risks might we be facing as we look to diversify away from a single choke point when you think about the global semiconductor industry into something that's a bit more distributed, right? Whether it's the US, whether it's the rest of the world, what are kind of the risks that we need to be mindful of that could either slow our progress or perhaps make this seem to be unachievable?
So I think the big thing is a risk in philosophy, or a risk in being conservative in a way. You have to be able to recognize that there's an extremely powerful technology out here that are these models. these AI models that we're seeing with large language models, and marrying those models to a mentality that a factory can be run with these same types of powerful algorithms. As soon as people realize that and see it in the world, it opens up enormous amounts of opportunity. The risk is if they don't see that, if they don't try, if they don't realize what is possible, that's the biggest risk. Is our own minds and our lack of imagination to realize that we have new tools available to us to do things differently.
I from time to time will think about how being an early stage VC, we need to retain a bit of our imagination, because not everything will be fully baked when a team comes to us and we invest in them. But having that imagination, that belief that this team can go realize and even grow their grand vision, is something that's super important. But even with the day-to-day, as we understand the power of LLMs better, there's a realization, oh, these could be applied in this situation. But when they're applied in this situation, where does the value really accrete? Is this really something we should invest in? Is it truly defensible? Why or why not? Right? Or is there a better way to kind of approach this back over here that we didn't originally think about because we were confined to our box, if you would?
Right. I mean, looking at the risk reward of an early stage investment into something that involves AI, manufacturing is, I wouldn't say an easy one, but it's an easy one to see how there are returns. If yield improvement on a semiconductor or any product in the world, it provides immediate value to customers. It's not some abstract business model where you're trying to think, how do you monetize a really cool idea? Manufacturing already has a monetization element built into it.
Yep, I think it's well put. So, I found your background to be fascinating. For our listeners, your undergraduate studies were actually focused on theater and music.
That's right.
You are a jazz pianist and composer. So I have to ask, how has your musical background influenced how you build and lead companies? Because surely there has to be some connection.
So people used to always ask me how it influenced my science, right? So this was always the question, and I spent years trying to think about this and trying to connect in my brain where that is. Now, how and I have some thoughts on that, but then I realized it's the same thing with the business. The important things that happen in business are things that happen in a out of the box creative way of thinking. So I play free jazz. I don't know if you're familiar with free jazz, but I play with bands that we go in having no idea what we're going to play. And it's all about listening. We play with our eyes closed, so that our auditory part of our cortex starts to recruit from the visual, so that we're doing things that don't even seem possible in physics, because sound moves only so fast, but yet we're collaborating and we're creating and we're building. This sort of empty space, this whiteboarding of ideas, this ability to dream and take that dream and very quickly turn it into a product, to go to the lab directly from the meeting that was an improvisational session and productize it, is like going from an improv session to a recording session. This is like, or going from a gig to it being on streaming or even on a record, which we still make. These things, when I realize that I get into the same frame of mind when I'm doing those two things. Now, obviously, a business day is not full of this type of creativity. It's full of all of the other things that are required to run a business. But from the innovation standpoint, there is a real connection, I think.
And I have to ask, because you mentioned it, how have you found that it impacts kind of the way you think through science and engineering? situations? Is it very similar because
Well,
you
yeah,
kind
I
of have
guess
that flow and
I guess
imagination?
I guess that was where I was getting at. That is, I finally figured out that it's the same. You know, I always avoided the question, how is your, well, the question was generally, how does a musical mind and a mathematical mind seem to be linked? There's a lot of musicians and mathematicians and physicists that do both. You know, I mean, Einstein played the violin.
Yeah.
So what is going on there? And I think that there is both a creative release that comes from playing music, and there's this recognition that you could do something that seems impossible to do. And
Mm.
when your mind enters that place, that's when you become creative. That's when you stop doing it. It ties back to our early conversation. Do you make chips the way that other people are making them? Do you fund the incumbents to make them the way that they've always made them? Or do you improv and seek what is that part of your brain that allows you to create very quickly and that almost doesn't make sense, and you can productize it quickly?
Amazing. Amazing. Well, I'm going to bring us home here, Matthew, and I like to finish with what I call rapid fire. I'm going to say 3 phrases, and I just want your 15-second immediate reaction.
Great.
Ready?
Sure, I'm ready.
The impact of the upcoming elections on manufacturing in the U.S.
Either way it goes, manufacturing is a priority.
The secular labor shortages felt by manufacturers, not just in the semiconductor industry, but broadly speaking.
There's a new type of labor that is open to everybody that I think makes people think about labor differently in the age of AI.
And then, I'm sorry I had to do this given the topic. What is your favorite flavor of chips?
My favorite flavor of chips, gallium oxide.
With that, this has been a really entertaining session and informative. I am really happy we were able to share your vantage points on a lot of the subjects that I think are going to be increasingly top of mind for global citizens. So with that, we look forward to your continued success at Nanotronics.
I appreciate the opportunity.
Thanks for watching. Follow us at dynamo.vc for all the latest episodes. We'll see you next time.